So if there's no questions on what we've been doing thus far, I decided that based on some of the questions that were asked that I probably ought to step back and some of you already know some of the terminology of steels, but I ought to go through a little bit more. So I was hoping to start weldability of steels, but I think maybe I'll just spend a little bit of time on terminology of steels. We talked before about cast iron, and cast iron was basically all we had except for a few very rare steels before 1856. In 1856, Sir Henry Bessemer learned that if you preheated the air coming into the furnace, you could melt steel by burning coal in air, and you could get temperatures of 2,500 degrees Fahrenheit if you preheated the air. If you don't preheat the air, the maximum temperature you can get is about 2,000 degrees Fahrenheit, and that won't melt steel. But Henry Bessemer invented the Bessemer converter, which basically blew the air in while the other exiting air was going out, and sort of preheated the air coming in, and he could get temperature sufficient to melt steel. In any case, we had cast iron because cast iron melts at a lower temperature than iron, pure iron. This is the iron carbon phase diagram. You've all got a copy of it, even if this thing's sort of washed out. But here's the melting point of cast iron, which according to this fine print is 1154 degrees centigrade. And the melting point of steel is about 1530 or 1538, it says on this diagram. Okay, so we don't have to worry too much about that, but there was steel before 1856. Anybody know where the steel came from? There were two primary sources of steel. One, meteorites from space that landed on the Earth were actually a lot of iron-nickel alloys with fairly low carbon. And if someone found a meteorite, they could hammer it into a sword. And that's why steel swords were fairly rare. The other thing is you could take cast iron and you could beat it and fold it over and forge it, just like kneading dough almost. Keep burning the carbon out. And if you don't burn all the iron out at the same time, you'll end up with some steel, okay? Lower carbon than 2 or 3% carbon or 4% carbon. And you'll end up here in the steel side. And there are three types of steel: low carbon, medium carbon, and high carbon that we call them today. There's no firm dividing line, but typically low carbon is something less than about 0.25%, less than 1/4%. Medium carbon is about 0.25 to 0.6, and high carbon is greater than 0.6, and you never go above about 1 or 1.1% carbon in steel. You actually can go higher if you look in this region, but you don't usually go much above 1%, which is right in here, okay? You can get 2% in here, but there's only some tool steels and other things have that much carbon. Together, this type of somewhere in the low and medium is often called, in a generic form, mild steel. Okay, someone mentioned mild steel. Well, mild steel is just slang for mostly a low carbon steel, but it could be pushing into the medium carbon steel. It's basically, mild steel is something that's easy to form, it's easy to weld, and we're going to learn that's because it's difficult to harden. Okay, it basically usually is in a particular crystal structure which we call ferrite. Someone else mentioned hot rolled versus cold rolled. And so sometimes you say, well, I have a piece of cold rolled steel. Well, what does that mean? Well, it means it came from a particular mill that can take hot rolled band, they call it, which is just a great big roll of like 1/4 inch thick steel. Let me back up. Steel is made by casting, in the old days, like 20-inch thick ingots and rolling them out. It's basically, they call breakdown rolling, and you forge it down to about 4 or 5 inches thick, and then you go through a hot mill. And a hot mill today might cost you $1 billion, today's terms, okay? A whole steel mill today might cost you $15 billion. And that's why no one has built a steel mill anywhere in the world since the 1960s. No company has built a new steel mill. They've always been countries that have built new steel mills. No company can afford the investment in their own steel mill. Okay? It was Bethlehem Steel in Burns Harbor, Indiana. Now it's part of ArcelorMittal because Bethlehem's bankrupt. Ever since I went to work for them, they went bankrupt. I guess I did it. I don't know. But anyway, Burns Harbor was the last company-built steel mill. All the others were basically built with government subsidies or whatever, because it's just too big an investment. We have the same types of things in the semiconductor industry. You know, Intel might build a $15 billion fab plant, but there's all kinds of politics and government subsidies that go with it. Boeing might start a new aircraft, and it's a $15 or $20 billion proposition. Well, there's all kinds of subsidies that come with those things too. Okay. In any case, steel mills are fairly expensive propositions. A hot rolling mill is about $1 billion facility, and you take these slabs, you put them in a furnace, you get them up to about 1100 degrees centigrade. Okay, so 1100 centigrade is up in this region, and you just put them through in 1100 centigrade, 1200 centigrade. The stuff rolls like butter. Now you're using cold. The rolls, the steel rolls that are rolling this, are cold, and they're rolling hot material. So you have to be careful about how you handle things, and you may water cool the rolls so they don't get too hot and things like that. But basically, you can break it down to about 1/4 inch thick, and that's hot rolled strip. And you put it in a coil while it's still hot and let it cool, and you call it hot rolled band. Okay, B-A-N-D. You take the hot rolled band and you take it over to another mill, which might be a $1.5 billion proposition today, which is called a cold rolling mill. And now you're basically going to put it through at room temperature through these big, massive rolls, and it'll be going through there at 60 miles an hour. And there'll be not just one set of rolls, great big rolls. There'll be about 6 or 7 rolls lined up, one after the other, so it comes in 1/4 inch, and it might come out at a 25 thousandths or 30 thousandths. No, you don't get any case hardened. I'll talk about case in a little bit. Case, you can get, well, actually, cold rolling should give you a nice uniform through the thickness hardness, okay, in general. But you can do other things to get local hardness, surface hardening. And I'm going to talk about that so far as that goes. But that's another thing. I mean, you got to remember, I told you, we know more about steel than any other material in the world, including silicon, okay? That's because it's a huge industry and it's had a lot of people working on it, so far as that goes. So that's some of the terminology. Anybody have any question on that terminology? So when you say hot rolled and cold rolled, now, if you're talking bar stock, I can have 1/2 inch bar stock, like this stuff. It's got a magnet in between. What do you know? I can have something like this 1/2 inch bar stock. That could be cold rolled because the mill to squeeze that could do it cold, even though it's a 1/2 inch. It might have started out with something that was bar stock of inch or 1.5 inch square, round or square. And a mill can have enough separating force to squeeze this cold down to this. But if you're talking big wide plate, 5 feet wide, the mill, we just don't have mills big enough to have the force necessary to squeeze that plate if it's more than 1/4 inch thick. So hot rolled, if we're talking plate material, plate comes off the hot roll basically, sheet comes off the cold roll. Okay? And it's basically just a question of thickness. When you get to bar stock, you can be a little bit thicker in the cold rolled. Hot rolled comes out annealed, and so the strength is 200 megapascals, 35 KSI. Cold rolled, you can come out with different hardnesses, and we sell it in the annealed condition. We sell it in the half hard condition or the hard condition. You can get 100 KSI out of a low carbon steel in the cold rolled condition, whereas you can only get about 35, 1/3 of that in the hot rolled condition, and it's a function of thickness, okay, coming out of the mill. Now we can also transform the steel by quenching it and tempering and doing other things, which is what I've written down over here, are some of the other terms. Ferrite. How did we get the term ferrite? Well, there was a metallographer, or actually there was a petrographer. Anybody know what a petrographer is? Any geologists here? Anyway, a petrographer is someone who polishes rocks and looks at them in a microscope to look for the different minerals in the rock. For example, granite is composed of 3 different minerals: feldspar, silica, and quartz. Yeah, silica, quartz. Feldspar, quartz, and something else. Okay, I can't remember the third. I'm not a geologist. Anyway, so Henry Sorby in England was a petrographer. He said, what if I do this with a piece of steel? And if you polish a piece of steel, you grind it smooth and polish it, you'll end up with a mirror. Doesn't look like much of anything. Well, he had the bright idea to etch it with some acid. And when he did that, it sort of goes frosty when you look at it with your eye. Put it in the microscope and you can see grain structure. You can see the individual crystals. Being a geologist, he said, well, it's an iron-based steel. And what do you call things that are iron? You use the Latin name of ferrite, okay, and you put "ite" in to make it a mineral name, okay? So this was ferrite. So low-carbon steel, the alpha form, the alpha form, which is from the phase diagram over here, is called ferrite. And it's unremarkable other than the grain size. Then later people had ways to heat the steel up and do other things, and they learned about this face-centered cubic phase at higher temperatures, and they named that austenite, again using the geology type stuff, after a British metallurgist called Roberts Austin. Okay, and then people had known for centuries you could heat the steel up into this FCC, quench it in oil, water. They didn't know about air quenching at the time. They didn't have the alloys. You could quench it in oil or water or a nice Nubian slave. One of the things the people in the Mideast used to like to do is they'd heat the steel up to its 1,000 degrees centigrade, and they liked to quench it in a live slave, okay, because it would give it virility to the steel. Didn't give much virility to the slave, but nonetheless, you can quench it in blood too if you want, okay? We don't do it much anymore. Anyway, so something they ended up finally calling the hard phase martensite after, I think he was Swedish. Martens was a metallurgist in the 1890s or so. And then bainite is a hard form of steel formed with a different crystal structure. And while martensite, if I were to take martensite, I could take a piece of chalk and snap it in two, and it's brittle. So is martensite in the as-quench condition. Bainite in the as-quench condition, you can bend it into a U, and it has almost the same strength as the martensite. It's because of a different type of transformation. Bainite was not discovered or understood until about 1930, and Edgar Bain was a metallurgist at U.S. Steel Research Laboratories, which later were called the Bain Laboratories, and bainite is named after Bain. You can quench in oil, water, or just let it cool in the air, which they call an air quench. And if you do that to martensite, it'll be glass brittle. Actually, it'll be about 10 times tougher than glass, but it's still pretty brittle, okay? You hit it with a hammer and it'll shatter. Okay, in fact, I think Mike Tarkanian does that in the forge down there. He'll take a piece of steel and he'll heat it up and quench it, and show that he'll show that before you quench it, it'll be nice and soft, and he can heat it up and he can bend it 90 degrees or 180 degrees, and then he quenches it in water and he hits it and makes sure nobody's looking in that direction. Everybody's got safety glasses on. He can shatter the bar. Okay, because martensite in the untempered condition is extremely brittle. I would say glass brittle, but it's not really glass brittle. It's about 10 times tougher than glass. In fact, cast iron is about 10 times tougher than glass. even though we think of gray cast iron as a very brittle material, and it is, it's just not as brittle as glass. But in any case, so questions? Cast iron pots is gray cast iron. If I took a sledgehammer to a cast iron pot, put your safety glasses on, wear your shin guards and other things, because shrapnel can go flying. Okay. But if you want to break one of the, in fact, if you've ever, well, you probably haven't seen it, but I've been there when they're digging up an old cast iron pipe in the street. They just get down there with sledgehammers and wham, wham, and break it apart. Because it's too hard to cut with a saw. It's easier to cut steel than it is to cut cast iron with all the hard particles and impurities in cast iron. Good soft cast iron cuts like butter compared to steel, but the old dirty stuff with all the impurities has got hard particles and just dull up saw blades. Okay, they often use carbide saw blades to cut cast iron, believe it or not, for old cast iron pipe. But big 36-inch diameter, water mains, when they have a break or something, they just go in there with the sledgehammers and these guys beat it to death. Okay, but wear your goggles and stuff, because when it breaks, it will shatter. Okay, it won't shatter like glass because it's tougher than glass, but it'll give off big brittle fractures. Okay, as far as that goes. Okay, so this quenched tempered. What else do we have in here? We have annealed, which I can take any of these steels and I can heat them up to just above this little line right here into the austenitic region and hold them there, and then cool them down slowly. Don't quench them in oil or water, and I will end up with an annealed microstructure, and it will be nice and soft. About 30 to 35 KSI yield. Depending on the carbon content, it can be 60 to 90 KSI tensile, so far as that goes. Okay, I can also normalize it. If I do that, I take it just above this line, heat it up, hold it there until it's uniform in temperature, and then I sort of forced air cool it, depending on the size of it. And because I'm going from FCC to BCC, if I cool it a little bit quicker than just letting it sit in the air over an hour or 2 hours or something, I can get a very fine grain size. It'll change from BCC to FCC to BCC. I'll get a fine grain size, and in most metals, fine grain means high strength, higher strength. And so let's tell a story. It's time to tell a story. Starting to doze off with all this technical stuff. So let's talk about bicycle frames, okay? Good old steel bicycle frames. We're not talking high-end titanium bikes or composite bikes like all of you like to play with. Let's just talk about the good old go to Walmart or Costco steel frame bike. It can be a mountain bike, it can be a trike bike, okay? It can be a tricycle or whatever, okay? Well, it's not a trike bike for what I was going to do. I was going to do 4130 steel, okay? To give you an example. Now, 4130 steel is also used for things sometimes called aircraft tubing, okay? 4130, the 30 tells you I got 0.3 carbon plus or minus about 0.04 or so. So it could be 0.26 to 0.34 carbon, because they can't hit it perfectly at the steel mill every time. 41 tells me something about the alloy content. In this case, it'll tell me something about the manganese that's in the steel. It'll tell me something about this particular steel. I think it has a little chrome in it, okay, like a third of % chrome, okay. So this is the alloy designation family, and here is the carbon level. So I got two numbers there, 4130. I stick them together. This is the American Iron and Steel Institute designation. It's been around for 100 years. You can have a 4140. You can have a 4135. 4130 is sort of garden variety, high strength steel tubing. Comes in three forms. If you look at the spec, quenched and tempered, annealed, and normalized. Quenched and tempered, it might have a strength of 120 KSI yield. I'll say 100 to 120, I didn't look it up. Yield strength, not much higher tensile strength. Annealed, it might be 70 to, well, let's just say, I'll just say it's 70 KSI. And normalized, it'll probably be 90 to 100. And so this is something that might be 3/4 of an inch in diameter, 1 inch diameter, might have a wall thickness of 1/16 of an inch, you know, think of a millimeter, 2 millimeters, something like that. You can make bicycles out of it. It's relatively easy to weld, okay? Some people would call this a mild steel. It's not really a mild steel, it's an alloy steel. It's got some alloying content to give us some of this extra strength and allow you to quench it and temper it. Because even in 2 millimeter thickness, a carbon steel might not always get quenched well enough to be hardened all the way through. You need something to slow down the transformation so that because the thing doesn't cool immediately when you put it in water. It takes a little time for the water to, you know, when you first put it in the water, you get boiling heat transfer on the surface, and that's not very effective. It takes a little time. It takes seconds for this to occur. And I don't always have seconds, okay? If I start looking at a steel transformation book, and I'm sure you all have these. I had this at home until I brought it in. A little light reading in the evening, okay? So here's a transformation curve for steel. Okay, let's see. It's probably better that way, I think. So here's the steel transformation curve, and it's time in seconds, log time in seconds versus temperature, linear temperature. This is well, I'm going to take it up here above, what's that, 1200? I can't read it. Fine, 1200, yeah. This is above 1200 Fahrenheit, so I take it up to 1300, 1350 Fahrenheit. This is doesn't even tell me the type of steel, but anyway. Okay. Anyway, I start cooling it. I can actually, what the metallurgists would do is they would quench it into a bath, a very thin strip, and hold it at some temperature. The bath might be a bath of hot lead, okay, at some temperature, and they'd measure the transformation. They really couldn't get things less than about 2 seconds because the thing won't quench that quickly. Okay, so that's sort of a dashed line. And this is the beginning of transformation. 50% line is this very barely visible line here, and the end of the transformation is here, and you get this characteristic C-curve behavior. And if you look at this temperature of transformation, this is the beginning of the transformation from face-centered cubic to body-centered cubic. There's the 50% point, and here's the end point, 100% transformation to body-centered cubic. This curve is called a sigmoidal curve, okay? If you're a metallurgist, you can study this for a whole semester, okay? Just that one curve. Enucleation and growth kinetics, okay? Ooh, how exciting. I had to do it once. Okay, but if you look at lots of different types of steels, you see that for a 1006 or 1008 steel, these things are transforming in less than 1 or 2 seconds, okay? If I add some alloy content to these things, and actually if I go to, this is a 1035 steel, and it's pushed over, the C-curve is pushed over to longer times, but I'm still dealing with times of less than 10 seconds for the transformation. If I get clever, I can start adding alloying elements. If I start adding, let's see if the light does better. If I'm adding molybdenum, this is 0 molybdenum. This is, I think I may have shown you this the other day, 0.15, 0.3, 0.38, and 0.5 molybdenum. And you can see the nose of the C-curve is getting pushed over from something that's about 2 seconds all the way over to 20 seconds. I can slow down the reaction by a factor of 10 by adding 0.5% molybdenum. So that's what I've done with 4130. I can't remember, I think it's chrome that they added to the 4130 to slow down the transformation so I can get all these wonderful phases that I would like. Okay, as a metallurgist. So I can buy the tubing in a number of different forms. So I'll tell you a story that relates sort of to welding and hydrogen and brittlement and stuff. So there was this kid in eastern Pennsylvania, and he was 21 years old, and he liked to do jumps with bicycles. So if you've been watching the Olympics and you see the people doing the slope, you know, these people are idiots, going up 300 feet in the air, doing, you know, 4 flips, you know, in the air. There was actually an article in the paper. One of these guys comes down on their head, and they're in trouble. Okay, they're dead. Okay, or worse. Well, this kid did the same. You know, he was doing flips on a bike. And he could ride the bike and put one of the pedals along the side of a rail. So if you see the people on these things, and they take their snowboard or whatever, and they slide down these rails up at the top and stuff. Well, he could do this with a bicycle, okay, and he could flip the bike and do a 360-degree turn in the air. Except one time he was doing it, and the handlebars came loose. And he landed on his head, and now he's a paraplegic. Okay. So I get the handlebars, 4130 steel. Turns out it was, pretty sure it was normalized. It wasn't special strength. Bicycle steels, you know, they're all about the same strength. This was a high-end bicycle. Okay, this was a jumping bike, and he had paid a lot of money for this special handlebar and stuff. But it was just a regular old tube that slips in. You know, the handlebars go this way. It's the tube here, and it had fractured. And it was a ductile fracture, except it had some fatigue early on, and it was nice chrome plated, of course, right, to make it look nice. And the problem was the final fracture was ductile. It wasn't brittle, but the beginning fracture was brittle. And what had happened? Someone electroplated it. When you electroplate the steel, you introduce hydrogen. The steel's embrittled. If that thing gets shipped to him, and he or whoever did it, they didn't bake out the hydrogen, and the steel's embrittled and it starts getting stressed within a few days or a few weeks, you have a brittle material, and it can start a crack. And it had started a crack, and it grew by fatigue until it was like 60% of the way around, and when on one jump the thing just broke. But the final failure was nice and ductile, the steel bent over and everything. Well, unfortunately the first part wasn't. So what happened here? There's nothing wrong with the steel originally from the steel mill, but there was something from the people in this little mom and pop shop in California who electroplated it. They didn't know that you had to bake out the chromium plate to get the hydrogen out. They just sent it to a plating shop, didn't tell them to bake it. The plating shop didn't say, oh, we should bake this. They should have. But they did it, sold it, and the guy's a paraplegic, yes.
So basically, if you want to electroplate something and still retain the strength, you have to put it in like an oven for a while?
Yeah, the ASTM specs say you must go from the electroplating bath to the oven within 1 to 4 hours, depending on the carbon content of the steel. Higher carbon steels, you got to get it in with 1 hour. Lower carbon steels can tolerate more hydrogen. You might take 4 hours. Nope, just an air oven. You're going to heat it 375 degrees Fahrenheit, typically. Okay, and they do it for either 1 hour in the oven, 4 hours in the oven, or 23 hours in the oven. Anybody know why they do 23 hours in the oven? Because you put it in at one time one day, you take it out an hour earlier the next day, and you put another batch in. It gives you an hour to change batches. Okay, that's why they say 23. But that's what the spec says, 23 hours. You say, well, where'd they come up with that? Well, if you keep on doing these every day and you made it 24 hours, eventually you get into quitting time. Okay, and people would have to stay over, right? So you want to keep using your furnace, so they make it 24 hours. Anyway, yes? Annealing basically cools slower. Actually, annealing, as I remember, you heat it up to a temperature above 900 C and cool it, whereas normalization, you heat it up just above this line. And normalization, you actually forced air cool it. You're getting better, faster cooling than annealing. Annealing, sometimes you actually anneal and just cool it in the oven, okay, in the furnace. It depends on the thickness of the part. But basically annealing, you're trying to get what we call a dead soft material. Normalized, you're trying to get a fine grain size. The purpose of the heat treatment is different. And you adjust your heating temperature and your cooling time in normalizing to get fine grain size. And annealing, you don't worry as much about the grain size, you're looking for softness, okay? So, and you're not looking for fine grain size, okay, so far as that goes. And so they have different names. Okay, so there's some bicycle tubing, and we use that same type of tubing to build small aircraft, and we have for about 80 years. That same 4130 tubing. If you go look at the aircraft that they were building, that they put canvas around in the 1930s, okay, to keep the wind out and stuff, or you go out to some small little place even today, there are people, you can buy kits of 4130 tubing and build your own aircraft. And as long as you don't take any passengers, you don't have to get special permission from the FAA. The Federal Aviation Administration will allow you to kill yourself or your family, but no one else, okay? If you're going to build it for other people to use, you have to follow all kinds of construction rules, okay? But if you're building it for yourself, it's okay to kill yourself. Which actually, I'll tell you another story. So, some people would like to own an F-15, you know, go Mach 2 or something like that. And they're fairly rich, but the government won't sell you a F-15 without all kinds of export controls. But some movie stars and others have enough money. They could buy the engine. And so there was this one company, that I don't know where they incorporated, but they were doing their tests in the Nevada desert. And it was called Peregrine Falcon. And I think they were selling these these aircraft for like $10 million or something. And basically, you just buy the engine from Pratt & Whitney or whoever. And it was the same engine basically it was the commercial version. I don't know if I want to say it's commercial version, because this one would go Mach 2. But it was a military engine, but it was sort of a commercialized version, okay, of the military engine that's in the F-15. And they basically would take some 4130 tubing or some aluminum tubing, and they put a seat in front of it, okay, maybe just a little bit above where the air comes in, okay. And then they put a skin around it and some controls and stuff, and they would sell it to you for, I can't remember, it was $10 or $15 million. But you had to come to Reno, Nevada, and you had to assemble half of it yourself, not the engine, but the airframe. And so, and there were some very famous movie stars who had bought this thing, and they were scheduled to come to this facility, and they were going to have some mechanics there and welders and stuff, and the movie stars would be able to buy their own Peregrine Falcon so they could go Mach 2 and get the thrill, okay? Because what's money, if you know. And so the first Peregrine Falcon, it blew up over the Nevada desert at 40,000 feet, and the test pilot was killed. And the second one, I got a call at 6 a.m. one morning, and the guy said, Tom, I want you to look at a Peregrine Falcon that crashed. This was the owner. He was now the test pilot. And I said, sure, when do you want to bring it by? He says, I'm down here at 77 Mass Ave right now. I said, okay, I'll meet you in the lab. So I came over here to right across from my office. My office was upstairs on the fourth floor back then. This is 20 years ago. And he brings in part of the empennage, the tail structure. And he tells me the story that this thing had crashed over the Nevada desert at 40,000 feet while they were doing the test flight. And they found wreckage strewed over 50 miles of the desert because you're that high going that fast. And he said he just brought in a part that he could bring in by hand. It's aluminum, so it's light. And he said, I want you to tell me why it crashed. I said, excuse me? I mean, how do I know that the bad part is here? He said, well, just look at it. So I looked at it and said, I don't see anything except overload. Okay, so he started telling me this theory that they thought maybe he had, at those speeds, you get into flutter. Okay, the wings start vibrating at supersonic speeds. And they thought maybe he got into flutter, and they had these little lead weights on the ends of the wings. He brought me the tail wing, not the main wings. And they thought maybe one of those lead weights had come off and they'd gotten into flutter because it didn't have the dampening weight. I said, well, why didn't you bring me that? He said, well, I can. So about 6 weeks later, they shipped me the end of the wing, both wings, and one of them, they had just glued about a 1 pound lead weight onto a little steel arm. Wasn't much bigger than that. And on one of them was still glued on. The other one is a very poor adhesive bond, and the lead weight wasn't there. I said, good theory, okay? That, you know, why they hadn't put a screw in to hold the lead weight. And if you want to adhesively bond it afterwards, but all you had to do was put a screw in it. But hey, so the FAA will let you kill yourself if you have enough money, and you can go Mach 2. And all those people who had put in, I think there was a $5 million down payment or something. That's how they were getting this stuff built. But all those people lost their down payment. But it was just petty cash for them anyway. Okay, so enough stories for today. Let's go into some of the other things on steels. We did talk about, or there's some questions about composition of steels. And I said steel is an alloy of iron and carbon. Whoops. Iron and carbon, we talked about you need manganese. And they learned you need manganese to tie up the sulfur because you always have some sulfur and phosphorus impurity. And what I did is I brought the manganese phase diagram for all of you phase diagram buffs. If I can get it to show.